An electric motor is an electrical machine that converts electrical energy into mechanical energy. The reverse of this would be the conversion of mechanical energy into electrical energy, and is done by an electric generator. In normal motoring mode, most electric motors operate through the interaction between an electric motor's magnetic field and winding currents to generate force within the motor. In certain applications, such as in the transportation industry with traction motors, electric motors can operate in both motoring and generating or braking modes to also produce electrical energy from mechanical energy. Found in applications as diverse as industrial fans, blowers and pumps, machine tools, household appliances, power tools, and disk drives. Electric motors can be powered by direct current sources, such as from batteries, motor vehicles or rectifiers, or by alternating current sources, such as from the power grid, inverters or generators. Small motors may be found in electric watches. General-purpose motors with highly standardized dimensions and characteristics provide convenient mechanical power for industrial use. The largest of electric motors are used for ship propulsion, pipeline, compression and pumped storage applications with ratings reaching 100 megawatts. Electric motors may be classified by electric power source type, internal construction, application, type of motion output, and so on. Electric motors are used to produce linear or rotary force, and should be distinguished from devices such as magnetic solenoids and loudspeakers that convert electricity into motion but do not generate usable mechanical powers, which are respectively referred to as actuators and transducers. History. Early motors. Perhaps the first electric motors were simple electrostatic devices created by the Scottish monk Andrew Gordon in the 1740s. The theoretical principle behind production of mechanical force by the interactions of an electric current and a magnetic field, Ampere's force law, was discovered later by André-Marie Ampère in 1820. The conversion of electrical energy into mechanical energy by electromagnetic means was demonstrated by the British scientist Michael Faraday in 1821. A free-hanging wire was dipped into a pool of mercury, on which a permanent magnet was placed. When a current was passed through the wire rotated around the magnet, showing that the current gave rise to a close circular magnetic field around the wire. This motor is often demonstrated in physics experiments, brine substituting for toxic mercury. Though Barlow's wheel was an early refinement to this Faraday demonstration, these and similar homopolar motors were to remain unsuited to practical application until late in the century. In 1827, Hungarian physicist Ennius Jedlik started experimenting with electromagnetic coils. After Jedlik solved the technical problems of the continuous rotation with the invention of the commutator, he called his early devices electromagnetic self-rotors, although they were used only for instructional purposes. In 1828, Jedlik demonstrated the first device to contain the three main components of practical DC motors: the stator, rotor and commutator. The device employed no permanent magnets, as the magnetic fields of both the stationary and revolving components were produced solely by the currents flowing through their windings. Success with DC motors. After many other more or less successful attempts with relatively weak rotating and reciprocating apparatus, the Prussian Moritz von Jacobi created the first real rotating electric motor in May 1834 that actually developed a remarkable mechanical output power. His motor set a world record which was improved only 4 years later in September 1838 by Jacobi himself. His second motor was powerful enough to drive a boat with 14 people across a wide river. It was not until 1839 that other developers worldwide managed to build motors of similar and later also of higher performance. The first commutative DC electric motor capable of turning machinery was invented by the British scientist William Sturgeon in 1832. Following Sturgeon's work, a commutator-type direct current electric motor made with the intention of commercial use was built by the American inventor Thomas Davenport, which he patented in 1837. The motors ran at up to 600 revolutions per minute, and powered machine tools and a printing press. Due to the high cost of primary battery power, the motors were commercially unsuccessful and Davenport went bankrupt. Several inventors followed Sturgeon in the development of DC motors, but all encountered the same battery power cost issues. No electricity distribution had been developed at the time. Like Sturgeon's motor, there was no practical commercial market for these motors. In 1855, Jedlight built a device using similar principles to those used in his electromagnetic self-rotors that was capable of useful work. He built a model electric vehicle that same year. The first commercially successful DC motors followed the invention by Zeno Graham, who had in 1871 developed the anchor ring dynamo, which solved the double-T armature pulsating DC problem. In 1873, Graham found that this dynamo could be used as a motor, which he demonstrated to great effect at exhibitions in Vienna and Philadelphia by connecting two such DC motors at a distance of up to 2 kilometers away from each other, one as a generator. In 1886, Frank Julian Sprague invented the first practical DC motor, a non-sparking motor that maintained relatively constant speed under variable loads. Other Sprague electric inventions about this time greatly improved grid electric distribution, allowed power from electric motors to be returned to the electric grid, provided for electric distribution to trolleys via overhead wires and the trolley pole, and provided control systems for electric operations. This allowed Sprague to use electric motors to invent the first electric trolley system in 1887–88 in Richmond, Virginia, the electric elevator and control system in 1892, and the electric subway with independently powered centrally controlled cars, which were first installed in 1892 in Chicago by the South Side Elevated Railway, where it became popularly known as the L. Sprague's motor and related inventions led to an explosion of interest in using electric motors for industry. While almost simultaneously another great inventor was developing its primary competitor, which would become much more widespread. The development of electric motors of acceptable efficiency was delayed for several decades by failure to recognize the extreme importance of a relatively small air gap between rotor and stator. Efficient designs have a comparatively small air gap. The St. Louis motor, long used in classrooms to illustrate motor principles, is extremely inefficient for the same reason. As well as appearing nothing like a modern motor, application of electric motors revolutionized industry. Industrial processes were no longer limited by power transmission using line shafts, belts, compressed air or hydraulic pressure. Instead, every machine could be equipped with its own electric motor, providing easy control at the point of use, and improving power transmission efficiency. Electric motors applied in agriculture eliminated human and animal muscle power from such tasks as handling grain or pumping water. Household uses of electric motors reduced heavy labor in the home and made higher standards of convenience, comfort and safety possible. Today, electric motors stand for more than half of the electric energy consumption in the U.S. Emergence of AC motors. In 1824, the French physicist François Arago formulated the existence of rotating magnetic fields, termed Arago's rotations, which by manually turning switches on and off. Walter Bailey demonstrated in 1879 as in effect the first primitive induction motor. In the 1880s, many inventors were trying to develop workable AC motors because AC's advantages in long-distance high-voltage transmission were counterbalanced by the inability to operate motors on AC. Practical rotating AC induction motors were independently invented by Galileo Ferraris and Nikola Tesla, a working motor model having been demonstrated by the former in 1885 and by the latter in 1887. In 1888, the Royal Academy of Science of Turin published Ferrari's research detailing the foundations of motor operation, while however concluding that the apparatus based on that principle could not be of any commercial importance as motor. In 1888, Tesla presented his paper A New System for Alternating Current Motors and Transformers to the AIE that described three patented two-phase, four-stator motor types. One with a four-pole rotor, forming a non-self-starting reluctance motor, another with a wound rotor, forming a self-starting induction motor, and the third a true synchronous motor with separately excited DC supply to rotor winding. One of the patents Tesla filed in 1887, however, also described a shorted winding rotor induction motor. George Westinghouse promptly bought Tesla's patents, employed Tesla to develop them, and assigned C.F. Scott to help Tesla. Tesla left for other pursuits in 1889. The constant-speed AC induction motor was found not to be suitable for street cars, but Westinghouse engineers successfully adapted it to power a mining operation in Telluride, Colorado in 1891. Steadfast in his promotion of three-phase development, Mikhail Dobrovolsky invented the three-phase cage rotor induction motor in 1889 and the three-limb transformer in 1890. This type of motor is now used for the vast majority of commercial applications. However, he claimed that Tesla's motor was not practical because of two-phase pulsations, which prompted him to persist in his three-phase work. Although Westinghouse achieved its first practical induction motor in 1892 and developed a line of polyphase 60 Hz induction motors in 1893, these early Westinghouse motors were two-phase motors with wound rotors until B.G. Lammer developed a rotating bar winding rotor. The General Electric Company began developing three-phase induction motors in 1891. Induction motor improvements flowing from these inventions and innovations were such that a 100 horsepower induction motor currently has the same mounting dimensions as a 7.5 HP motor in 1897. Motor construction. Rotor. In an electric motor, the moving part is the rotor, which turns the shaft to deliver the mechanical power. The rotor usually has conductors laid into it which carry currents that interact with the magnetic field of the stator to generate the forces that turn the shaft. However, some rotors carry permanent magnets, and the stator holds the conductors. Stator. The stator is the stationary part of the motor's electromagnetic circuit and usually consists of either windings or permanent magnets. The stator core is made up of many thin metal sheets, called laminations. Laminations are used to reduce energy losses that would result if a solid core were used. Air gap. The distance between the rotor and stator is the air gap. The air gap has important effects, and is generally as small as possible, as a large gap has a strong negative effect on the performance of an electric motor. It is the main source of the low power factor at which motors operate. The air gap increases magnetizing current. For this purpose, air gaps should be small. Very small gaps may pose mechanical problems in addition to noise and losses. Windings. Windings are wires that are laid in coils, usually wrapped around a laminated soft iron magnetic core so as to form magnetic poles when energized with current. Electric machines come in two basic magnet field pole configurations: salient pole machine and non-salient pole machine. In the salient pole machine, the pole's magnetic field is produced by a winding wound around the pole below the pole face. In the non-salient pole, or distributed field, or round rotor machine, the winding is distributed in pole face slots. A shaded pole motor has a winding around part of the pole that delays the phase of the magnetic field for that pole. Some motors have conductors which consist of thicker metal, such as bars or sheets of metal, usually copper, although sometimes aluminum is used. These are usually powered by electromagnetic induction. Commutator. A commutator is a mechanism used to switch the input of most DC machines and certain AC machines, consisting of slip ring segments, insulated from each other and from the electric motor shaft. The motor's armature current is supplied through the stationary brushes in contact with the revolving commutator, which causes required current reversal and applies power to the machine in an optimal manner as the rotor rotates from pole to pole. In absence of such current reversal, the motor would brake to a stop. In light of significant advances in the past few decades due to improved technologies in electronic controller, sensorless control, induction motor, and permanent magnet motor fields, electromechanically commutated motors are increasingly being displaced by externally commutated induction and permanent magnet motors. Motor supply and control. Motor supply. A DC motor is usually supplied through slip ring commutator as described above. AC motors commutation can be either slip ring commutator or externally commutated type, can be fixed speed or variable speed control type, and can be synchronous or asynchronous type. Universal motors can run on either AC or DC. Motor control. Fixed speed controlled AC motors are provided with direct online or soft start starters. Variable speed controlled AC motors are provided with a range of different power inverter, variable frequency drive or electronic commutator technologies. The term electronic commutator is usually associated with self-commutated brushless DC motor and switched reluctant motor applications. Major categories. Electric motors operate on three different physical principles: magnetic, electrostatic and piezoelectric. By far the most common is magnetic. In magnetic motors, magnetic fields are formed in both the rotor and the stator. The product between these two fields gives rise to a force, and thus a torque on the motor shaft. One, or both, of these fields must be made to change with the rotation of the motor. This is done by switching the poles on and off at the right time, or varying the strength of the pole. The main types are DC motors and AC motors, the former increasingly being displaced by the latter. AC electric motors are either asynchronous or synchronous. Once started, a synchronous motor requires synchronism with the moving magnetic field, synchronous speed for all normal torque conditions. In synchronous machines, the magnetic field must be provided by means other than induction, such as from separately excited windings or permanent magnets. A fractional horsepower motor has a rating below about 1 horsepower, or that is manufactured with a standard frame size smaller than a standard 1 HP motor. Many household and industrial motors are in the fractional horsepower class. Notes: rotation is independent of the frequency of the AC voltage. Rotation is equal to synchronous speed. In SCIM fixed speed operation, rotation is equal to synchronous speed less slip speed. In non-slip energy recovery systems, WRIM is usually used for motor starting but can be used to vary load speed. Variable speed operation. Whereas induction and synchronous motor drives are typically with either 6-step or sinusoidal waveform output. BLDC motor drives are usually with trapezoidal current waveform. The behavior of both sinusoidal and trapezoidal PM machines is however identical in terms of their fundamental aspects. In variable speed operation, WRIM is used in slip energy recovery and double-fed induction machine applications. A cage winding is a shorted circuited squirrel cage rotor. A wound winding is connected externally through slip rings, mostly single-phase with some three-phase abbreviations. BLAC, brushless AC, BLDC, brushless DC, BLDM, brushless DC motor, EC, electronic commutator, PM, permanent magnet, IPMSM, interior permanent magnet synchronous motor, PMSM, permanent magnet synchronous motor, SPMSM, surface permanent magnet synchronous motor, SCIM, squirrel cage induction motor, SRM, switched reluctance motor, SYRM, synchronous reluctance motor, VFD, variable frequency drive, WRIM, wound rotor induction motor, WRSM, wound rotor synchronous motor.